In this problem, we have a point charge of mass 9.6 times 10 to the negative 2 kilograms and charge 6.77 microcoulombs that is suspended by a thread between two vertical plates of a parallel plate capacitor. The sphere is pulled towards the right plate, and the thread then makes an angle of 22 degrees with respect to the vertical. If the separation distance between the two plates is 0.025 millimeters, the question asks us to calculate the potential difference or the voltage difference between the two plates of the parallel plate capacitor. So we'll go ahead and start off by drawing a free body diagram for the point charge. Let's think about all the forces that are acting on the point charge. For starters, we have the force of gravity pulling the sphere down towards the ground. We can calculate that force of gravity by multiplying the mass of the sphere times the free fall acceleration g. So this is going to be 9.6 times 10 to the negative 2 kilograms multiplied by the free fall acceleration of negative 9.8 meters per second squared. And this is going to give us a force of gravity, or a weight, equal to negative 0.9408 newtons. And the force is negative because it's directed downward. And what's preventing the sphere from falling is the tension in the thread. So the thread pulls up towards the upper left-hand corner of the screen, parallel to the thread. And that force that the thread exerts on the sphere is called the tension force, T. Now, we don't know what that tension force is, but we do know that that tension force has both an x component and a y component. Additionally, the sphere is pulled towards the plate on the right by an electrostatic force. So we're going to go ahead and draw that electrostatic force pointing towards the right. So in other words, the sphere is simultaneously repelled by the plate on the left and attracted by the plate on the right. So we can go ahead and break up the tension force into its components. So the tension force will have both an x component and a y component. To break up the tension force into its components, we'll go ahead and draw a right triangle. So we'll have a component that's parallel to the y-axis, we'll call that ty, and we'll have a component that's parallel to the x-axis, we'll call that tx. And this angle here that the thread makes with the vertical was already given. That's 22 degrees. And since the sphere isn't moving, we can assume that it's in mechanical equilibrium. And in mechanical equilibrium, all the forces in both the x and the y directions have to add up to 0. So let's think about the forces that are acting in the y direction first. We have the force of gravity pulling down, and we have the y component of the tension force pulling up. So in order for that sphere to be in equilibrium, those two forces have to add up to 0. So Ty plus negative 0.9408 newtons has to equal 0 in order for that sphere to stay stationary. So this now allows us to calculate the y component of the tension force. So in order for the sphere to stay stationary, the y component of the tension force is equal and opposite to the force of gravity, so that's going to be 0.9408 newtons. Based on this y component and the angle that the thread makes with respect to the vertical, we can now calculate the x component of the tension force. So let's go ahead and redraw the triangle here. So this is the thread that pulls on the sphere with a force T. And we know that the y component of this tension force is 0.9408 newtons. And the x component is unknown. So we'll just go ahead and write that as Tx. And the angle that the thread makes with respect to the vertical was given in the problem, that's 22 degrees. And this is a right angle here. So we can now use trigonometry to figure out what the x component of this tension is. And notice how the x component is directly across from the 22 degree angle, which means that the x component is the opposite side to that angle, 22 degrees. The y component is next to the 22-degree angle, so that's the adjacent side. So we can make use of the tangent function to figure out what the x component of that tension is. So we can say that the tension of 22 degrees is the opposite side, which is Tx, divided by the adjacent side, which is Ty, but we already know what that is, 0.9408 newtons. So we can go ahead and calculate Tx by multiplying both sides by 0.9408. So we have Tx is equal to 0.9408 newtons multiplied by the tangent of 22 degrees. So we have Tx is equal to 0.380 newtons. So now that we have the x component of the tension force, we will be able to find the electrostatic force acting on the sphere. If you remember from the free body diagram, we had the force of gravity pulling down, and that was negative 0.9408 newtons. We had the y component of the tension force, which was equal and opposite to the force of gravity, canceling out the force of gravity, so that's going to be 0.9408 newtons in the upward direction. Pulling the sphere to the right, we had the electrostatic force, which is unknown. We'll call that Fe. And then the x component of the tension force was pulling to the left, and that x component we've just found to be 0.380 newtons. And since that force is directed to the left, we'll go ahead and make that negative. Now, in order for the sphere not to move and for it to be in equilibrium, not only does the sum of forces in the y direction have to be 0, but the sum of forces in the x direction also has to be 0. So we can go ahead and add up the forces in the x direction and set that sum equal to 0. So we have the electrostatic force acting on the sphere plus negative 0.380 newtons, that's the x component of the tension force, and all of that has to equal 0. So if we move this term over to the right side, we have the electrostatic force acting on the sphere is equal and opposite to the x component of the tension force. So that's 0.380 newtons. Now we know that this electrical force is exerted on the sphere by the electric field created by the two plates. Since the sphere is positively charged, it will be simultaneously repelled by the positive plate and attracted to the negative plate. So we can then figure out which plate is positively charged and which plate is negatively charged. So since the positively charged sphere was attracted to the plate on the right and repelled by the plate on the left, that means that the plate on the right is negatively charged and the plate on the left is positively charged. And that is because the sphere is positively charged, so it's going to get attracted to the negative plate while simultaneously being repelled by the positive plate. And so this parallel plate capacitor generates an electric field that goes from the positive plate to the negative plate. And that electric field now exerts an electrical force on the sphere. And since that sphere is positively charged, the electrical force acting on that sphere due to the electrical field is in the same direction as the electric field. So since the electric field points towards the right, the electric force also points towards the right. So we can calculate the electrical field, E, by dividing the electrical force exerted on the sphere by the charge of the sphere. So the electrical force that the electric field exerts on the sphere is 0.380 newtons, and then we're going to divide that by the charge of the sphere, which was given in the problem. That was 6.77 microcoulombs, and a microcoulomb, remember, is 10 to the negative 6 coulombs. So this ends up giving us the strength of the electric field. So that gives us 56,129.99 newtons per coulomb. So that's the strength of the electric field generated by the parallel plate capacitor. But given the strength of that field, we can now calculate the voltage difference between the plates. So the electric field of a parallel plate capacitor can be written in terms of the voltage difference between its plates. And the formula goes as follows. The electric field of a parallel plate capacitor E is just the voltage difference between its plates divided by the separation distance between its plates. And since we know the separation distance between the plates, because it was initially given in the problem, and we've just calculated the strength of the electric field generated by the parallel plate capacitor, we could use these two pieces of information to calculate the voltage difference between the plates of the parallel plate capacitor. So in other words, if we multiply both sides by D, we have that the voltage difference between the plates is equal to the electric field strength, E, times the separation distance, D, between the plates. So we have 56,129.99 newtons per coulomb. And then we're going to multiply that by the separation distance, which was given to be 0.025 meters. So we end up with 1,403.2 volts.